Hello and welcome to this third lesson in this series on metric and topological spaces. In this lesson we're going to be looking at functions, and as always in the description is the booklet for you to download and follow along with. So let's have a start by looking at some simple examples of functions, or things that look like functions that you would have seen in your earlier maths journey. So here we just have f of x equals x squared. And this function, it takes any value of x and it gives you a single value for y. But now let's have a look at this second example. So we have a circle here, and even though we can draw a graph of this, it's not actually a function. We can't write it in the form f of x equals something. And we can see that because if we take this value of x here, where does it go? There's no value of y for that value of x. But then also, for this value of x, there's two different values of y we could have. So the one on the left is a function, because for all x, we just get one value out. But the example on the right isn't a function, because some values of x return nothing, and some values of x give us two values for y. Now we can look at a formal definition of a function. So if a and b are sets, then a correspondence that associates to every element x in a single element f of x in b. This is called a function or a map from a to b. So that is, it takes every element of a and returns a singular element in b, just like the x squared function did. And to say that a function is a function from a to b, we can write it like this. And this is read as f maps a to b. At this level, we don't know exactly what f of x does. We don't know exactly what that value or the output's going to be. We could determine that by an equation we're given, or we could, if we had finite sets, just draw arrows from one list of elements to another list of elements, or something like that. Okay, so this value, f of x, we call the value of f at x. Then the set A, so the set we're mapping from, is called the domain of the function f. And then the set B, the set we map to, is called the domain, the codomain, or the range. On this slide, I'm going to put up some example and counterexamples of functions. Then it's up to you to decide whether or not they are well-defined functions or not. And then I'll obviously go through the answers. And there is space in your booklet for you to write yes, no, and write a quick explanation. So let's look at our first one. So here the domain is the open interval from -2 to 2, and the codomain is the total set of real numbers. And this takes an x in the domain and returns the square root of 4 minus x squared. So is this a function? So yes, this is a function, because for every value of x in that domain, so every value of x from -2 to 2, does return a single value if you put it into that square root. Note that it doesn't matter that we don't have an x that gives every single value in the codomain. We didn't actually have really any reference to the codomain in the definition apart from what the set was. So it doesn't matter if there are values or if there are real numbers that don't get mapped to. What matters is every value in the domain has a well-defined output. So let's have a look at our next example. Okay, this is not a function because any value of x greater than 2 or less than -2 will not have an output. Okay, this is also not a function even though it does have that square root is well defined for everything in the domain, the plus or minus sign means for every value of x, we have two different outputs. Remember, a function only allowed one output. Okay, let's look at this function between finite sets. And you see here, I've told us what the function does just with arrows from one set to the other. So is this a function? And yes, this is a function. Every value 135 in the domain is mapped to just a single value in the codomain. And it doesn't matter that 2, 6, and 7 don't get mapped to, and it doesn't matter that 3 gets mapped to twice. What about the last one? So this is not a function. The reason is 3 there doesn't get mapped to anything. So we don't have an output for every value in the domain. So now let's look at the idea of a graph. You're probably used to graphs. In fact, we saw them at the start of the video, where you have an x-axis and a y-axis, and you draw out all the points that satisfy a particular function. The intuition here is a little bit similar, but we have to be a bit more formal in our definition, particularly since we're dealing with potentially arbitrary sets. So the formal definition of a graph is the subset of A cross B. So remember, A was the domain and B was the codomain. And this is defined by the set of points x and f of x for all x in A. And this set of points, x, f of x, these are just the coordinates you would plot when sketching the graph. So let's look at an example. So what is the graph of this function? So we see 1 gets mapped to 3, 3 gets mapped to 3, and 5 gets mapped to 1. So our coordinates would be 1, 3, 3, 3, and 5, 1. Okay, what would the graph be of this function? Now I'm going to give you a minute or so, or you can pause the video to have a go on your own. So the graph of this function is 1, 1, 3, 6, 5, 2. So now we're going to see a way we can categorize functions into 3 groups. So the first type of function is surjective or onto, and a function is surjective if for all b in the codomain there exists at least one a in the domain such that f of a equals b. So in other words, the function gets mapped onto the entirety of the codomain. Our next type is injective or into, and this is true if all distinct points a and alpha get mapped to different points in the codomain. So in other words, every single value gets mapped to a unique point. There are no two values in the domain that get mapped to the same point. Another way you might see this written is f of a equals f of alpha if and only if a equals alpha. And then the last type is bijective or one-to-one if it is both surjective and injective. So every point gets mapped to a unique point in the codomain and the entirety of the codomain gets mapped to. And in this case, we can pair up elements in the sets A and B. And if we can match them up, or we can pair them up, then the two sets must have the same number, and if all we're talking about is number of elements, the two sets are equivalent. On this slide, I'll put up some functions, and it's up to you to decide whether they're bijective, injective, surjective, or none of those. And these should be in your booklet, and there's some space to write down your thoughts and your answer, and you can also pause the video after I put up the function before I give you the answer. So the first function is here. We see that A gets mapped to 1, B gets mapped to 2, and C gets mapped to 2. Well, this is none of them, so it's not surjective because nothing maps to the value 3, which is in the codomain. And it's not injective because both B and C get mapped to the same value, 2. Okay, the next function here. This is bijective. And we can see that because every value in the domain, every real number gets mapped to a unique real number as the output. And for every real number, we can find an x that maps to it. So it is bijective. Then what about this? Okay, so this is injective. So the reason it's no longer surjective is because we're now mapping between the naturals. And because of that, nothing maps to 0. X would need to be -1, but that's not in the domain. So nothing gets mapped to 0. And then finally, this one's a bit more complicated. But this is once again bijective. So now we've seen functions, let's look at the inverse of a function. So we have a function that maps A to B. Then the inverse maps B to A, and it's defined such that if we take the inverse and then apply the function again, we get back to where we start. Or similarly, if we take f of A and we apply the inverse, we get back to A. So it just takes a point, we map it to whatever it goes to in B, and then the inverse maps it back again. There's a diagram of that here. So let's look at a quick example. We have, if f of x is 2x, then if f inverse of x is x over 2. So you can see that f of 3 is 6, and then f inverse of 6 is 3. Or if f equals x squared, now we can't invert this. What does 4 go to? It could go to 2, or it could go to -2. So there's no inverse, or there's no singular inverse of 4. And then also, where does -1 go? So the inverse is only defined for bijective functions. Although sometimes what you can do is restrict your domain and codomain so that it's just bijective on a subset of both. We are now going to look at the image and pre-image. So this is essentially we're asking what happens if we try to apply the function to our set or a subset instead of just single points. So firstly, let's look at the image. So if f is a function that maps A to B, then if big X is a subset of A, then f of big X is a subset of B that contains all the points f of little x, where little x is in big X. And this is then the image of X. So we can write this formally. F of big X is equal to all the points f of x, where x was in the original subset big X. And we can see this visually. If here's our subset big X, then we can map that into B, and we get f of big X. But we're really just mapping every point one at a time, and then the final image is just all of those combined. And then similarly, we have a pre-image. So if y is a subset of B, then the pre-image of y is the subset of A that contains all the points little a, such that f of A is in y. And we can write that as the pre-image of y is all the points A, such that f of A is in y. So we take set y and we map it back. And basically we're just finding all the points in A that would get mapped into Y. Okay, we're now going to go through and find some images and pre-images. I'm just going to go through, put up each question, and then I'll put up the answer a second or two later, so you have some time to think about it. So let the set A equal ABC, let the set B equal 1, 2, 3, and we have a function that sends f of A to 1, B to 2, and C to 2. So what is the image of this? This should be the set containing 1. Remember, it's a set. So taking the image, so it would be the set containing 1 and not just the point 1. What about this? And then what about the pre-image here? So that's the set BC, because both of those things get mapped to 2. Then this. So nothing gets mapped to the point 3, so the pre-image of this is empty. And then our second example. So what would f of the image of the set containing the point 3 be? Be the set containing 9. The inverse, or the pre-image of the set containing 9, would be 3 and minus 3. So remember, both points get mapped to 9. Then the pre-image of this closed interval be here, so we have the positive and negative solutions there. And then finally, and this here is an open interval, not a coordinate. So the image of that is here. And notice it's closed on the left-hand side, so it's closed at 0. So 0 is included in the image, but 1 is not. We're going to go through a couple of examples, and as per, I'll go through the first one, and then I'll put the second example up, and you'll have time to do it on your own. I'll put the answer up on the video. So, firstly, we take an arbitrary x in f of x intersect y. So we take an arbitrary point in that image. Then there exists a y in x intersect y such that f of y equals x. Note there could be more than one point that satisfies this, but for now we're only looking at one. Since y is in x, therefore f of y is in f of x. And similarly, little y is in big Y, and therefore f of little y is in the image of big Y. Therefore, f of y is in f of x intersects f of y, and therefore x is in f of x intersect f of y, because remember, f of y equals x. And since x, the initial point we picked, was arbitrary, this holds for all x in f of x intersect y, and therefore it holds in general, and therefore f of x intersect y is a subset. Okay, for the next one, prove this. I'll give you a couple of minutes, and then you can come back to the video. Okay, now you've had a go, I'll put the answer up. And again, we need to use that line at the end. Since x is arbitrary, this holds for all x and therefore holds for the sets. Also, note that we haven't just said y equals f inverse of x, because, as I said before, there could be multiple y's that satisfy this. We know at least one y exists, because x is in the image of f of x, or f of y. So we know one point exists, such that f of y equals x. However, we can't just say little y is the inverse of little x, because there could be more than one. If f was bijective, then this would be much easier to prove, and we could just use the inverse. But without knowing that, we have to be a little bit more careful. So we've seen both the pre-image and the inverse, but they're very easy to get mixed up and confused. So let's have a look at what the differences between these two things are. So the pre-image, we act on sets, whereas the inverse function acts on elements. And the pre-image is always defined. It could just be empty or it could contain multiple elements, but is always defined, whereas the inverse is only defined for one-to-one or bijective functions. So let's look at an example here. We can calculate the pre-image of 0, which is just the set containing 0, and we could work out the inverse of 0, which is 0. We could work out the pre-image of 4, which is the set containing -2 and 2, but there's no inverse of 4. Similarly, if we want to do the pre-image of -1, well, this is the empty set. But again, there's no point that is the inverse of this, so it's not defined. We're now going to be looking at compositions of functions. So this is essentially where you apply a function and then apply another function to the output. So if f maps a to b and g maps b to c, then there is an element g of f of a, which is in C. So we take the point A, we apply the function f to it, and that gives us an element in B, and then we apply g to that, and that gives us an element in C. And we can write this composition of functions as g circle f. And this function g circle f maps A to C. And we would say g circle f as g after f. So the function on the right always acts first. And to keep this clear in our heads, we can draw diagrams to show this. So here we've got the function f mapping from A to B, the function g mapping from B to C, and a function h mapping from A to C. Now, if h is equal to g after f, then this is called a commutative diagram. So commutative just means the order doesn't matter. So if h is equal to g after f, then it doesn't matter whether we go straight from A to C or whether we go A to B, then B to G. Then B to C. Here's another one. See, we have f maps A to B and k maps B to D. And h maps A to C and g maps C to D. And in this case, if g after h equals k after f, then this is commutative. So then it doesn't matter whether we go A, C, D or whether we go A, B, D. And finally, here, if we have f maps A to B and f inverse maps B to A, then we have, if these are well defined, then we have the identity function that maps A to A, and it just maps every point to itself.